go ahead and get started. Get the mic far away from the speaker so we don't get the feedback. Okay, so the first talk today is Learning Scheduling Models from Event Data by Arik, Kyle, and Chris, and Arik will be giving the talk.
Thank you for the introduction. Feedback? We start? Hello everyone, my name is Arik Senderovic from University of Toronto. I'm going to talk about learning scheduling models from event data. This is a joint work with Kyle Booth and Chris Beck. So our motivation is coming from schedule-driven processes, schedule-driven systems where we actually execute a schedule as part of our daily lives. So for example, timetables in public transportation, or you can think of production plans in manufacturing settings, or appointment books in hospitals, in outpatient hospitals. This is going to be our motivation. So in these systems, in order to produce good schedules, we want to have good models. And basically, in order to get those models, we will typically have an OR expert or an OR analyst coming into our system, into our organization, conducting interviews, sending around some industrial engineers to do time studies, collect their measurements, and then make some ad hoc modeling decisions as to how a good scheduling model should look like. Okay? However, there are some problems with this approach. First of all, it's time and resource consuming. Secondly, we often get inaccurate measurements because measurements can become subjective, especially if we ask the experts how long things take. And the modeling expertise of our OR analyst matters. So if the OR analyst is an expert, we will get good models. If not, we will get worse models. So the question that we were trying to answer in this work, and I hope that you will be convinced that the answer is positive, can we automatically create a scheduling model that would be evidence-based and would kind of overcome these three limitations? Now, we're going to use a model learning approach. So we're assuming that when a schedule is executed in our manufacturing setting, our modern information systems collect everything into event logs or event data. And then we're basically want to learn from this data, we want to learn a scheduling model that would hopefully enable us to optimize the process or the system. And we're making two assumptions. The first assumption is that the system is already executing, otherwise we don't have data. And the second assumption is that our data contains only positive examples, only feasible solutions. And this makes sense because that's how real-life data looks like. What is event data? I just want to give you an example. This is a hospital example. We have cases or jobs running through the process. These can be patients in the hospital. So here, patient 1 is performing an activity type called blood draw by resource registered nurse, and it has the real execution time, start time and end time. This is not the scheduled time. They can be different. And every row is basically called an event. That's why we call them event logs or event data. Now, I'm going to introduce the field of process mining, which is where I come from. Process mining is all about trying to mine event data and to elicit processes that describe the system. Typically, we mine Petri nets, which are executable models that contain time, and time can have distribution, et cetera, et cetera. And these models so far have been used for descriptive analysis to show the management how my system looks like, or for predictive analysis to try and simulate Monday morning and see how many doctors we need, for example. It has not been used for scheduling, so in a sense, in this work, process mining meets scheduling, and we're going to employ process mining to learn the models. All right, so our approach is as follows. We will take an event data, we will mine a timed Petri net, and we will convert this timed Petri net into a scheduling model. Now, in this work, we refine the notion of scheduling model, and we separate the problem description, which is a parameterized model, from the CP model, the constraint programming model that is actually going to solve our problem. Okay? So in the remainder, after giving you an introduction, I'm going to talk about the details of our contribution, show some proof of concept experiments to our approach, and conclude with future work. Now, our contributions are as follows. So first of all, we were going to talk about the basic scheduling problem, which is our problem description. It's a declarative problem description. We're then going to talk about how we're mapping those basic scheduling problems to CP models. Then we're going to define a new type of Petri nets, which is a subtype of timed Petri nets called activity resource Petri nets. We will see why we need these creatures. And then we're going to map these ARPNs, or activity resource Petri nets, to basic scheduling problems. And overall, our contribution is kind of an end-to-end solution that takes in data and produces a scheduling model. So these are our contributions. And here's a definition of a basic scheduling problem. I'm going to TLDR it for you in the next few slides. It generalizes some well-studied scheduling problems, job-shop scheduling, parallel machine scheduling, et cetera, et cetera. It has two main components. The first component is instance-based. So whenever we get a new set of jobs that contain activities and we want to schedule them, this is an instance-based thing. This is not something that we learn, right? We have the next 50 patients that we need to schedule. And we assume that we know the types of the activities and the jobs. So for example, the first job here is patient 1 that has two activities, A1 and A2, but we also know their types. So A1 is type blood draw, and A2 is type examination. We have a second patient, A3, that has activities A3 and A4. And A3 stands for exam, A4 stands for infusion, and we also have types to those patients. So the green patient here is a consulting patient, and the blue patient is an on-treatment patient. So basically, we know activities and their types. The second part of the basic scheduling problem is a parameterized part, and that's the part that we're going to learn from event data. All right? So what does it have? It has precedence constraints between activity types per job type. So for the orange type, consulting patients, we're going to have blood draw preceding exam. So we need to finish doing the blood draw activity in order to perform an exam activity. That's an example. We're going to learn the resources and their capacities. So basically, for example, here we have 4 medical doctors and 3 nurses available. And we're going to learn the assignments, possible assignments between resources and activities, and how long these assignments take. And we're learning deterministic models, so we're going to use averages to represent durations. Now, once we have the BSP learned, we're mapping it to a CP model, to variables and constraints. Basically, activities are mandatory interval variables, a very standard representation in scheduling problems. Then the precedence constraints are represented by end before start constraints. So blood draw must end before exam starts. And then we have the resource assignments represented as optional interval variables with resource-dependent durations. So if this exam is performed by a nurse practitioner, it's going to take 15 minutes. And if it's performed by a doctor, it's going to take 20 minutes. And finally, we have resource capacity enforced by cumulative global constraints. And at the end, we get a CP model that is standardized. It's kind of expert independent. And however, we don't have guarantees on its quality. So potentially, we could have a better model coming out of this if we have a highly expertise modeler that comes into the system and creates the model. Another thing to note is that we do not we do not learn an objective function. So a user has to provide an objective function in order for our approach to eventually solve the scheduling problem. So far, we talked about the description of the scheduling model, what it means, the separation between the problem and the model. Now we're turning to the data side of things and how we're learning and representing the data using timed Petri nets. So what is a timed Petri net? I'm not going to go a lot into the detail here. It's a well-established formalism to model dynamic systems. It's more than half a century that Petri wrote his PhD thesis, and these models have been used ever since. So rectangles in our models represent transitions or actions, and the labeled transitions are essentially transitions that have durations. So for example, exam here, the activity type exam here is represented by a labeled transition, and it's going to be associated with a certain duration. The black transitions, the silent transitions, are routing transitions. For example, for the second construct, let's try to point, we're going to have a decision whether this infusion is going to be performed by a registered nurse or by a nurse practitioner. Now, we also have circles or places. These are essentially buffers that can contain either activities or resources. Okay? And the rule is that circles can only be connected to rectangles and vice versa. So we cannot connect rectangles to rectangles and circles to circles. Now, the edges correspond to preconditions and effects, and the distribution of tokens essentially represents the system state. So here we have a state of nurse practitioner ready to serve this activity, and the registered nurse is also ready to serve. However, there's no activity that it can serve, so the next execution will be an exam by nurse practitioner. Now there's a gap because our basic scheduling problems are less expressive than a general timed Petrinet. For example, a timed Petrinet can model shared resources, non-unary demands, etc. So in order to map our Petrinets to a basic scheduling problem, we need to restrict the timed Petrinets. And the way we're going to do it is to define our own subtype of Petrinets called activity resource Petrinets. They're basically defined inductively as follows, so we only allow the gray constructs that represent activity types. We call them in the paper seize delay release constructs. They seize a resource, they delay it together with the job, and they release the resource, essentially. Then we have the blue area, which connects several of those activity types, and they correspond to job types. And finally, we have the resources that can only connect to activity types. So basically, by this definition, we have ARPNs that are a limited version of the TPNs. We do not allow anything that the timed Petrinets can allow. Now, for mining TPNs from event data, we use an existing algorithm by us from BPM 2015. And the algorithm basically looks at temporal dependencies between activity types. If we have overlaps or precedence constraints, it also looks at the distribution of durations. However, we take mean values here because we're doing deterministic scheduling, and we learn the resource capacities and activity assignments as part of that algorithm. Once we have a TPN mined, we need to make sure that it's an ARPN, and in the paper we provide a polynomial time algorithm that does that, essentially by decomposing the Petrinet. Then we need to map those ARPNs into BSPs. So here's one example. We have the Petrinet that corresponds to the on-treatment patient that does exam and then infusion. What we do is using graph algorithm, we detect that there is a dependency between exam and infusion, so an exam must end before an infusion starts. Then we have, and the exam must be performed by a nurse practitioner because this is the only resource connected to this activity type. And we detect that the infusion can be performed by both NP and RN. And the durations of infusion is going to be inferred from the Petrinet, essentially, from the transitions associated with durations. Now, you can find the technical details of this algorithm in the paper. I'm not going to go into this. And to the proof of concept of our approach. So the first proof of concept, we have standard benchmarks, standard job shop scheduling benchmarks. We simulate them to create event data, and then we apply the approach. Learn the time Petrinet, learn the basic, convert it to a basic scheduling problem, create the CP model, and use CP optimizer with a 10-minute time limit to solve the scheduling problem and get a schedule. And we're interested in two comparisons here. Does my basic scheduling problem correspond to the way that the JSP is defined? And the second comparison is whether my CP model is good enough, because I told you that we made several design choices along the way, and maybe a better modeler that would sit on the, consider the model for half a year could come up with a better CP model. So as for the results, the BSP learning for the 53 benchmarks that we learned for takes less than 1 second, and the BSP that we get is exactly equivalent to the JSP. Now, the CP model was able to solve 49 of the 53 learned models to optimality in an average time of 15.4 seconds, and it found feasible solutions for the other 4 instances with an optimality gap of 6.3%. That is after 10 minutes. For the second proof of concept, we took real data. So we're working with a real hospital in Boston. The data that we used is 4 months of data with 30,000 activities happening per month. 240 job types, 60 activity types, and we applied our approach till we got a CP model that we solved again using CP optimizer with a 10-minute time limit. By the way, for the JSP, we used the makespan, and here we're going to use both makespan and sum of completion times, and I'll tell you why. And the question here is whether my CP model is good enough, but also we have the ground truth schedules of that hospital, so we could compare how well we're doing with respect to what the hospital is doing, essentially. So for the results, we didn't have a BSP ground truth, but we were able to learn, using the 3 months of data, we were able to learn within 450 seconds the corresponding BSP model. We used 1 month of test data in April, so we had 21 working days that we used to compare our approach. The CP model, essentially we solved 21 instances from April by learning over the first 3 months. So with minimum make span, we solved to optimality all test days within 1 second. And this is because this hospital has very long activities that took over the make span. So we moved to sum of completion times, and here the success was not as great. Although we were able to get feasible solutions for each of the 21 days, we had quite a notable optimality gap of 50%, but we did find feasible solution for all days. And lastly, comparing our schedules to the real hospital schedules, we executed our schedule. We drew the durations from a distribution, and we had punctuality for patients, so patients could be early or late. And essentially, this is sum of completion times over the 21 days in April. And this is the comparison. So our approach is in red, and the hospital schedule is in blue. As for future work, we are now working on learning scheduling models with objective functions. And we actually want to extend the BSP to include more complex representations. Thank you, and if you find this interesting, please read the proceedings. Thank you so much.
Thank you for a very nice talk. I think it's very impressive work. Regarding the objective functions that you learn, you evaluated your solutions now on the some of the completion times, and you do very well, I think. But are other objectives that you could have considered that you maybe do poorly on in this case?
That's correct. So we limited ourselves to make span and sum of completion times. Sum of completion times kind of corresponds to also minimizing the waiting time in that hospital, so that's what we took. But we don't learn the objective function, right? That's work in progress.
Let me refine that. What are other examples of objectives that you did not consider, but that the hospital would find also interesting?
So, for example, the proportion of cases that the hospital had to close after 6 o'clock, so right, overtime kind of objectives. So this is also very important. Resource utilization is important for that hospital, so yeah, definitely. Yeah.
2 questions. One, in your graphical representation, I guess NP and RN are resources, like you said. Have you considered the fact that some activities can be accomplished using different resources? So either a nurse or a doctor can perform a blood test, for example.
Right. So this is essentially what we see in the second construct here, right?
Yep.
So infusion can be accomplished by either a registered nurse or a nurse practitioner. So is that what you're asking?
Yeah, that was my question. Thank you. The second question I've got is, can you prioritize activities? So once they come in, so for example, if something like this were to be implemented in a hospital OR, you would have, depending on the priority of the case that comes in, you would want to prioritize activities. Is that something you've considered, attaching priorities to different activities?
So you could extend the basic scheduling problem with that, but we would need more data, I guess. We would either need to infer priorities or have priorities explicitly in the data. Right? That's a good idea on how we can extend the BSP.
Thank you.
Thanks.
I think we have time for one more quick question. No? Okay, thank you very much. Next talk. Very good. Next speaker. Excellent. Okay, the next talk is efficiently exploring ordering problems through conflict-directed search. Jinkai Cheng, Cheng Fang, David Wang, Andrew Wang, Brian Williams. All right, Jinkai Cheng is going to be giving the talk this morning.
Hi everyone, I'm Jinkai Chen. Today I'm going to talk about efficiently exploring ordering problems through conflict-directed search. This is a joint work with Chen Fang, David Wen, Andrew Wen, Brian Williams at MIT Merce. So this paper proposes an algorithm called conflict-directed incremental total ordering, CDITO, to efficiently order multiple goals for planning and scheduling. So first, let's look at an example. In this example, we have 3 tasks: task A, task B, and task C. And the start and end are the events 1, 2, 3, 4, 5. We may have some time windows over these tasks, as well as some temporal constraints, such as the whole mission should be completed within 70 seconds. So if we only have this temporal constraint, it's a temporal constraint network. We have specialized algorithm for it. But in the real-world problem, there are a lot of state constraints. For example, if task A and task C are competing over resources, it becomes a job shop scheduling problem. And the more complex example can be each task is to schedule and route some data flows for serialized network. In this case, we need to handle routing with resource constraints. And in manufacturing, for manufacturing robots, we need to consider motion planning. And for scientific exploration, we need to plan for multiple goals over long horizon. And we need to consider both motion and resources and a lot of other requirements. So in these problems, the state and the time are always coupled with each other. And it's always very heavy to check the state constraints, which is like whether 2 episodes can be concurrent or in sequence. And we don't know it beforehand. So we want to avoid this kind of heavy state or temporal consistent checking as much as possible. So we propose such an algorithm called conflict-directed incremental total ordering, CDITO. CDITO takes a set of partially ordered tasks, and it generates a total order of these tasks. And it gives this task and a total order to subsolvers like some routing or temporal consistency algorithm to check whether it's consistent or not. If it's inconsistent, some ordering conflict will be summarized and give to the CDITO and generate another total order until we find a consistent total order. So in this case, and we have a total order first, and we give it to subsolvers, and we repair our total order with respect to the ordering conflicts. So CDITO takes as input an ordering problem, which has 3 elements. The first element is event. So we have 5 events in our motivating example. And also, we have ordering relation, which is a set of clauses. Each disjunct of a clause is a partial order. In this case, we have 4 clauses, and the first 3 clauses force the start to precede the end. And the last one means the task C or task B should precede task A, which are extracted from the temporal constraints. And also, we have this consistent checking function, and it takes a total order of all the events, and it outputs whether it's consistent, and if it's inconsistent, the ordering conflicts will be output. So the consistent checking function H represents subsolvers. It can be defined by users, and as long as it can return some conflicts. So the solution of this ordering problem is a total order that respects all the ordering relations and the consistency defined by the subsolvers. And this CDITO mainly combines 2 ideas. The first idea is the total order tree that arranges all the total orders in a special tree structure. And the second idea is to apply conflict-directed search within this tree structure. So this tree structure was proposed by Ono in 2005 and brought into this community by David Wan and Brian Williams in 2015, which was first used as an ordering module in a temporal planner called Tiburton. So first, let's look at an example. We have 4 elements, 1, 2, 3, 4, 1, 2, 3, 4, and the root total order of this tree is 1, 2, 3, 4. And we expand this tree by taking some integer and redshifting it. First, we take 1, and we redshift after 2, after 3, and after 4. We get 3 total orders. And we take 2 and redshift after 3 and 4. And we take 3 and redshift after 4. So these are all the children of the root total order. So in this tree, a very interesting thing is that we have a notion of level. So intuitively, level is for total order. The level of this total order is the first integer that is not in the right place. For example, 2, 1, 3, 4, the first integer should be 1, but it's 2, so the level of it is 1. And the level for 1, 2, 4, 3, the first 2 elements are in the right place, but the third is not, so the level of it is 3. So we restrict our child expansion to such a way that is the children of a total order should have a level that is less than its parent. So basically, the level always decreases when we just search when we search deeper. In this case, level 2 total order can have level 1 children, and level 3 total order can have level 1 and level 2 total orders. So the interesting part about this is that we can arrange all the total orders in such a tree. And we also define a notion that is order move. So order move is an edge, the operator in this tree. And an order move, I to j, is to move the ith element right after the jth element. So we apply some search in this total order. So the search basically follows 2 rules. The first rule is we use depth-first search, and it always visits children before its sibling. And we also visit children by redshifting smaller integers. So let's have a look at this example. From 1, 2, 3, 4, we take 1 first and redshift it until the end, and we take 2 here, and we visit its children first, and when its children have been exhausted, we visit its sibling. And we explore this tree in such a way. And this is very important for our conflict direct search. So we just do a search. So by using this tree structure and this search strategy, we have very good property. So if we have some constraints such as 1 before 3 and 2 before 4, and when we find some total order violates a constraint, we can prune it. So in this case, when resolving a conflict requires a level more than the current level, its descendants, siblings, and the siblings' descendants can be pruned. It makes sense because the level always decreases when we search deeper. So let's take a closer look at this subtree. From 1, 2, 4, 3, we visit 1, 4, 3, we visit 1, 4, 2, 3. And 1, 4, 2, 3 violates 2, 4. And as we can see, this 4, 2 violates 2, 4, and it exists in all its children, all its siblings, and all its sibling descendants. So we can safely prune them. The reason is as follows. Moving 4 after 2 is required to satisfy 2, 4. But unfortunately, 4 cannot be moved in the subtree rooted from 1, 4, 2, 3 and a sibling because of it has level 2. And for a sibling, if we just move it much farther to the right, and 4, 2 still exists. So this is the basic idea of how to apply conflict direct search in this subtree. Sorry, in this total order tree. So in this tree, we are working with disjunctive total ordering or disjunctive total orderings. And the conflict-directed process is as follows. We resolve, we compute a resolution for each single ordering conflict, and we combine them together to get the to get a resolution. So here is a case for resolve a single conflict. We have a notion of first resolution. The first resolution of an ordering conflict from a total order is the first order move that negates at least one partial order in this ordering conflict. So basically, if we just do the search by following that order, and there is an order move, and that can negate the ordering conflict to make to make this ordering conflict to not hold in the total order. And for example, here we have 3 types of resolutions. The first type is moving the integer less than the level. So this resolution directly moves to its children. And also for type 2, we move the integer that is the level. And it just redshifted much further, and we get to its sibling. And the third type is moving the integer larger than the level. So if it's in this case, we can do the pruning just in our previous example. So if we have the resolution for single conflict, and we can combine them to compute the multiple conflict resolution. For example, here, 1, 2, 3, 4, 5, it has 2 ordering conflict. For each ordering conflict, we have a resolution. And in this example, the resolutions are 1, 2, 3, and 1, 2, 4. And we will choose 1, 2, 4 as our resolution, because if we choose 1, 2, 3, and the second ordering conflict cannot be resolved in the subtree, and we just jump much further. And this pruning is complete. And also, when we resolve conflict, we consider the search state. For example, so the same example, but this time, the last order move is to move 2 after 3. But the resolution should be 1 after 4, right? But the last order move tells us every order move before that have been determined to be inconsistent by our previous search. So we can just follow the depth first search and use the order move 2 after 4. So basically, this search combines all the ordering conflict and search state is complete and also systematic. And we can also extract ordering conflict from subsolvers. And that's a way CDITO to interact with subsolvers. We have 2 examples. For state inconsistency, if task A and task C cannot overlap, we can use this ordering relation that is to force every start end to be before the end, which represents this concurrency. And we just give it to CDITO, and it can be handled. So for temporal inconsistency, as we know, for simple temporal network, checking the temporal consistency is equivalent to finding the negative cycle. And if some temporal constraints imposed by ordering relations, we can just imposed by ordering relations are involved in this negative cycle, we can just collect them and put them into an ordering conflict and give it to CDITO. So we have introduced the search, the tree, and the conflict extraction. Here is a complete example of, this is a complete process of running algorithm on a motivating example. Here, we start here, and we do the conflict directed search. And we find it's consistent with respect to all the ordering relations, and we give it to subsolver. Subsolver detects some state inconsistency in the last slide, and it just gives to CDITO, and we search again. And we find a temporal inconsistency, we give it to the CDITO, and we do a search until we find the solution. So in this example, we have 120 total orders, but only 1 total order is consistent. And we do 8 iterations, so CDITO only spent 8 iterations to find the solution, and only call the subsolver 2 times. Yes. Okay. And now here's the results. We benchmark our algorithm over the temporal network configuration scenarios. In these scenarios, we need to consider we have a bunch of data flow requests. We need to consider the source, the destination, and the bandwidth, loss, and delay. Basically, it's very heavy to check whether 2 data flows can be concurrent or not. So we set a timeout at 20 seconds and compare against the ITO, which is the predecessor of our algorithm. And then we can see CDITO can solve most of the problems in 20 seconds. ITO can only solve 5 of them. And even if the network, we have 50 network flows, and CDITO is able to solve 74% of them in 20 seconds. So now let's conclude. So CDITO is incremental and systematic. It can systematically explore the search tree, and it can also interact with the subsolver through the ordering conflicts. And the main idea of it is to apply conflict direct search in a spatial tree structure. And in the future, we would like to integrate ITO with some hybrid planners. And we'll also explore the best first search version for CDITO. Thanks for listening. I'm happy to take any questions.
Can you go to slide 8, please? Vehicle routing problems and the Agile Earth Observing Satellite problem have a bad trait that the cost of transition between, say, 4 and 2 can vary depending on where it appears in the sequence. Does this approach presume that the transition time is constant regardless of where the activities appear in the ordering?
So it really depends on the consistent checking function. So in this, so our algorithm currently is only able to solve the satisfaction problem. So if you have a cost and this kind of thing, and if you can put it into the subsolver, and it'll be fine. But it depends on how you define the subsolver.
Okay, thank you.
I think we have time for one more question. I have a comment more than a question. The search you're defining reminds me of what was referred to probably 20-ish years ago as discrepancy search, where a heuristic provides you with what look like your orderings, and then you ask yourself, can I deviate from that ordering? And I don't think that there's a real question here, and I'm not expecting you to know work that's 20 years old, but I may follow up with a question on that later. So thank you very much.
Thanks.
The next talk is an MDD-based Lagrangian approach to multi-commodity pickup and delivery. Margarita Castro, Andre Agostino-Sina, and Chris Beck. This is one of the journal track papers, and Margarita will be giving the talk this morning.
So I just connected the HDMI. Can you please change the source of the slide projector? It was working before. Ah, there it is. Okay. Now it should appear soon. Okay. I always have technical difficulties in my presentations. So thank you for the introduction. I'm Margarita Castro, and I'm going to present this work that I said together with my supervisors, Andres Irea and Chris Beck. And well, the title is MDD-based Lagrangian approaches to the one-to-one MPD TSP. And I hope that by the end of the presentation, you can actually understand what the title is, because it's kind of cryptic. So let's start. So in this talk, we're going to, in this project, we tackle vehicle routing problems. And usually these type of problems are solved using mixed integer programming approaches. But the main problem is that we usually have a large number of constraints, even exponentially number of constraints. And the linear programming relaxation sometimes is not very informative. It can be very weak. And this is even worse when we start adding extra constraints to the problem. So if we have precedences or time windows. So our idea was, well, what happens if we use, instead of a linear description of the problem, a discrete representation of the problem? So the approach is as follows. What we're going to do is that we have a relaxed multi-value decision diagram approach, We're trying to represent the whole set of solutions using this multi-value decision diagram. And then we're going to use it to compute bounds and add it to a branch and bound procedure. So it's the same as using, for instance, MIP or CP, but now how we guide the search is by these relaxed multi-value decision diagrams. So the specific problem that I'm going to talk about is the one-to-one multi-commodity pickup and delivery traveling salesman problem. It's very long, the name. So the idea is that we have a set of locations that we want to visit, and the thing is that we're going to have M commodities that we have to pick up and delivery. And since we want to visit each location only once, we're going to basically be enforcing some precedence constraints. We can't visit a location where we have to deliver something before going to the other location where we have to pick up the object. And also, the commodities have different weights, and the vehicle has a limited capacity. And the objective in the end is to visit each location once in a single tour such that the total distance is minimized and we satisfy all the constraints of the problem. So this is how we're going to represent the problem using multi-value decision diagrams. So as you can see, okay, I'm not going to try. So the main idea is that we have this graphical structure that has a root node in the top and a terminal node in the bottom. And each of the paths are going to we're going to have one path for each of the possible tours. And some of them are going to be infeasible because we're basically constructing a relaxation. So the main idea is that we have this variable pi t that represents which is the location that we visit at time step t. So the graph basically starts with the first layer, that is the first location that we visit, that in this case is always location 1. Then the second layer is which is the second location that we visit, and so on. So for instance, here we have a little example. This is actually the optimal solution for this small problem. So it goes from location 1, 4, 2, 3, and 5, and we can see the path also in the decision diagram. And the cost is basically the cost that is represented by the distances between the nodes. So what we are going to do is that we're going to compute the shortest path in this decision diagram using the traveling distance of our instance here to get a lower bound, basically an admissible heuristic, or depending on which community you are, which is the name that you use. So yeah, in this case, since we're minimizing, this is just a lower bound of our problem, and we will use this throughout the search. So one of the important things about the relaxed MDDs is the construction. So the bigger the graph is, the better bounds that we can get. So here we have one that has a size 1 because it has one node per layer, and here a size 2, and we can see that the lower bound significantly improves. But also, what is very important is how we construct these graphs. So here I have two relaxed MDDs. Both of them have the same size, but the bound is quite different. And all this depends on how we made the decisions of how to construct these relaxed MDDs. And you can see that actually the one in the the last one is the one that gives us the optimal solution. So now I'm going to introduce our construction procedure. It's very simple. It's an iterative procedure. We start with a very simple MDD, just with one node per layer. And iteratively, we start increasing until we reach our maximum size that we want this graph to be. And we have two main procedures. The first one is filtering. The main idea is that we want to, as we make the graph bigger, we start identifying some edges that represent infeasible solutions, so we can remove them. It's basically logical inference rules. And the refinement is basically rules that tell us how to split the nodes to try to represent some combinatorial structure of the problem. And here we use some of the filtering and refinement rules that were already in the literature for sequential problems. So we use a permutation and rules for precedence constraints. But also in this work, we develop new rules now based on the capacity restrictions of our vehicle that end up being a very important part of the problem. And also we have a capacity-based refinement procedure. So I'm going to go a little bit more detail how we construct these multi-value decision diagrams for our example. So as I said before, we start a very simple with one relaxed MDD. And now in the second layer, we can already start removing some edges. So if you notice, as I said before, you always start in location 1, but we can't go to location either 3 or 5 because they are delivery locations. So we can just remove them from the graph right away. And then what we do is that we split, in this case very simple, 1 node per each of the 2 decisions that we have. And now we can start removing more edges. So for instance, So for instance, here, we made the decision, we start location 1, now we're in location 2. And now, well, if we already visit location 2, we don't want to visit it again, so we can just remove the arc. And we don't want to visit location 3 because we haven't picked up the object in that location. So we do this iteratively, then remove the edges, split, remove edges, split until we are done. So now I'm going to explain one of our main contributions. That was this capacity refinement procedure. So the main idea is that we want to try to represent this constraint as best as possible inside of relaxed MDD. So we're going to group all the nodes such that the vehicle load in that specific stage is the same. So I'm going to show a little example. So at the beginning, we assume that our vehicle starts with load 0. We haven't picked up anything. But after we visit location 2, we have picked up the object here that has weight 3. So the load of the vehicle is 3. And here, we go to location 4. The load of the vehicle is 2. So then if we continue on up to this node, is the decision either you go to location 2 or 4 and 2. So they are together because the load of the vehicle is the same. And the nice thing about this procedure is that we can guarantee that we can represent the capacity constraint of the vehicle if we have we need at most the capacity plus 1 nodes to represent this constraint exactly. So if we use this construction, at least we're sure that we're not violating this constraint, but of course we can violate other ones. So here, as I said before, like even if we use a smart construction to try to represent some constraints, we might violate other ones. So even with the capacity one, we might violate the presence and the tour constraints, and this can impact significantly our lower bound or the quality of the heuristic, basically. So here, for instance, even though this graph was before giving us the optimal solution, there are some paths that are infeasible. So here, going location 1, 4, 3, 4, 3. So we're skipping 2 locations, and we're repeating 2 locations twice. And it also has another infeasible path there. So what we propose is, well, we have this discrete representation. We also wanted to combine it with all the theory and benefits of using linear programming. So we propose a hybrid method that combines the MDD and an IP formulation of the problem. And we use a Lagrangian duality to mix these 2 techniques. So here is the IP problem. I'm not going to explain it too much, but the main thing is that we have a bunch of constraints representing all of the characteristics of the problem. And there is a specific set of constraints that we identify that our relaxed MDD might violate. That is basically that we don't visit each location once. Sometimes we don't visit them. Sometimes we visit more than that. We can violate the capacity, and also we can violate the precedence. So we focus on these specific constraints, and we want to somehow tell the diagram when we violate these constraints. So this is where the Lagrangian approach appears. So basically what we want to do is to somehow introduce the information of the linear constraints into the decision diagram, and we do it via dual information. So it's very simple. We just penalize the objective function by the constraints that we know that they might violate. And then what we do is that we compute our shortest path again, but now with the penalized objective function. And to compute which are the optimal penalties, we just solve the Lagrangian dual problem. That is an iterative problem of give me some multipliers, I check them, then give me better ones, and so on. So here is a small example of how this works. Here we have our relaxed MDD, and the blue lines is just the shortest path, and we can see that it's violating the constraint of visiting each location once, because we visit location 5 2 times. And well, if we use our Lagrangian penalties, the objective function will look something like that. And in fact, if we choose the penalties correctly, we can now get actually the optimal solution of our problem. So we penalize visiting location 5 too many times, and now the shortest path gives us the optimal solution. This is not always the case, but at least in this example worked perfectly. So we get the optimal. So to summarize our approach, we have a branch and bound tree search procedure. We use the MDD to compute the bounds, and we're going to get the optimal Lagrangian multipliers at the beginning of the search. We use the bundle method to do this, and then we use the same Lagrangian multipliers throughout the search because it was very expensive to compute them all the time. And we update the MDD depending on the decisions that we have done, that our tree search has done. So instead of results, I wanted to first show the bound qualities. So here we have in the x-axis what is the bound if I don't use Lagrangian, and here what is the no bound gap when I use it. So the smaller gap, the better. And we can see that all the points are below the diagonal, so that means that actually using Lagrangian relaxation was helping us to get better bounds. And in fact, we were able to reduce the optimality gap up to 30%, so we have like a huge improvement using this technique. And now I wanted to show you how it compares if we use this whole thing and compare it to the state-of-the-art approaches. So we have like the classic thing that people in OR do, Bender's decomposition, branch and cut. We tested 2 different ways to construct these decision diagrams with size of at most 1,024 nodes per layer. And we have a bunch of instances, 527, that correspond to symmetric, asymmetric TSPs. It has a little bit of everything, and to our limit. So here is the main results. We have instances, symmetric TSP with 47 locations, and symmetric TSP for up to 30 locations. And we can see that our Lagrangian approach, it didn't matter that much which construction we used. They were outperforming by far the state-of-the-art, that is the Benders and the branch and cut. But also the nice thing is that even without the Lagrangian, we were already beating the state-of-the-art, but the Lagrangian helped us to solve even farther, like a bigger number of instances. And in terms of time, here I divided the instances depending on the capacity of the vehicle. And one of the things that we noticed is that when the capacity is very small, usually the problems are harder. It takes more time to solve them. And in these cases was when our capacity-based compilation was really, really good. And when the restriction was more, we had more capacity, the restriction wasn't that high, it didn't make that much sense to use our specific construction. So something more general that it was already in the literature was performing much better. So to summarize, well, I present you how to use relaxed MDDs to solve this specific vehicle routing problem. We improve our relaxation by introducing dual information and using Lagrangian relaxation, and we close 27 open instances in the literature. So yeah, you can look at our paper in our webpage, and it's going to be soon in the Informs Journal of Computing. Thank you.
Thank you for a very nice talk and nice work. I have a question on your branch and bound. You have an outer branch and bound, and each node you have your MDDs that you, I assume, recompile at each time. Why don't you define your branch and bound on the MDD nodes? So you have every state can be put into a queue, and then you just process those, like was done in other work on MDDs.
I'm not sure if I understand the question. So it's not like let me show. So our specific implementation, we implement our relaxed MDD as a global constraint in constraint programming. So we basically constructed one, and then the solver like keeps the memory and updates us throughout the search. So it's not like we constructed from scratch every time that we need the relaxation. I'm not sure if that's what you were trying to.
I see. That would be so you implemented in CP Optimizer, I assume.
Yes.
Okay. Well,
yes.
my question is, if you look at the last exact layer in the MDD, rather than implementing this inside CP Optimizer, the last exact layer or the frontier, you can take those states, put them in a queue, and process them one by one. So rather than having an outer search, you basically build your queue based on the one MDD, and you process them one by one. But maybe we should take this offline.
Yeah, maybe we should take it offline. But basically, during the search, we try to also guide the search with respect to the information of the MDD. So we do a depth first search, and we follow the shortest path of the MDD too. So it's not just like jumping around. We try to use the structure as much as possible to guide the search.
Hey, thank you for the talk. I'm supposed to keep it quick, so just a very quick one. The multipliers, are they associated with a single move or with a full path?
Okay, let me go. I'm not sure if I understand the question. So the idea is that the multipliers are associated with a specific constraint. So for instance, in this case, each multiplier is associated with a specific location in our problem, but depending on the constraint that we relax, this might look a little bit different, and we also try relaxing multiple constraints at the same time. But in this one specifically is related to the location, so that's why here we didn't penalize any of the other locations, we just penalized the one that we knew that was giving us problem, that was location 5 that we were visiting too many times.
So does that mean you can consider each multiplier in a single node in the MDD?
No, so the multipliers in the end it just add to the cost. So it's like we add like an extra cost to each of the edges of the MDD, it's not to the nodes of the MDD. Okay?
Thank you very much. All right, last talk in the session, a stochastic dual dynamic integer programming for the incapacitated lot sizing problem with uncertain demand and costs. And our Franco Quezada is our speaker this morning.
Margarita, do you have the pointer? Thanks. Okay, I think we need to switch again the source. Okay, which is okay. So, thank you for the introduction. Well, my name is Franco Quezada. I will present to you now the work that I carry out together with my supervisor, Céline Jiquel and Safia Kedat-Sindou. Well, basically, I will try to solve. I will show you a really classical problem in operation research, which is the stochastic incapacitated lot sizing problem. And we are trying to use a different approach, which wasn't used before in the literature. As I know we have an audience that maybe don't know too much in this kind of problem, I will briefly introduce this problem in his deterministic version. Then I will show you how we manage the answer types in this problem. And then I will try to give you the main step of which is an stochastic dual dynamic programming. And if everything goes well, I will show you some computational results. So what's the ULS, the incapacitated load sizing problem? In this problem, we look for planning production activities over a finite time period horizon. Let's be T, capital T, the final time period horizon, and we can define the following variables. Xt is defined as the quantity that we can produce at each time period. Yt is the setup variable, which takes the value 1 if we produce in the time period t, and 0 otherwise. And st is the inventory level at the end of each time period. And this variable leads to the following MLP formulation that we want to minimize all the involved costs, the setup costs, inventory holding costs, and production costs. And we have a set of constraints where basically the first one linking the production variables x with the setup variable y. The second one is the inventory balancing constraint and has an implicit constraint that says that all the demand must be satisfied at each time period. And then we have the domain of the variables. Well, this formulation was first introduced by Werner Within in 1958, long time ago. And we know that this problem can be solved in polynomial time. But when we consider uncertainty in this problem, we have really a different history. So we assume that all the parameters in this problem are subject to uncertainty and completely unknown. The parameters are the demand and the production cost, setup cost, and inventory holding cost. And we assume also a multi-state decision process to modeling the stochastic process. And this is based on a scenario tree representation. So let me introduce some concept. The first one, I will try to give you some ideas of the scenario tree. For example, in this one, we assume that this is the first stage of the multi-stage stochastic decision process. And we have to make a decision x1, which is the production decision. And also, we have a demand realization of the uncertainty parameter. Then, with some probability transition, we move to a second stage when some of the uncertain parameters, we have a new realization of the uncertain parameters, and we have to, again, make decision for each one of them. And we continue the process by some probability transition to move on a new stage and take a new decision for each of the possible realization of the uncertainty parameter. And we do that until to reach the time period horizon. So using this representation, we have a new formulation from the problem, which is called an extensive formulation. We have basically the same definition for the variables, but instead of has a decision variable for each time period, now we have decision variable for each node into the scenario tree. So we have a much more larger formulation for the problem. And as I told you, the deterministic version can be solved in polynomial time, but this stochastic version is actually NP-hard, was proven in 2009. And most of the work that I carried out trying to solving this problem was based on the study the polyhedra or the linear programming formulation, providing new validities inequalities and using in a framework of branch and bound or branch and cut algorithms. The problem, as I told you, is the size of the formulation depends strongly of the number of nodes in the scenario tree. And the number of nodes in the scenario tree grows exponentially fast with the number of time period that we want to plan it. So most of, well, actually all the implicit enumeration methods fail try to solving the problem for large scenario tree. Why we need a large scenario tree? Basically because if we want to have a good representation of the stochastic process, we need to have a good or a huge scenario tree that will be represent this process. So we want to propose an alternative formulation for this problem, which is a dynamic programming formulation. Instead of take all the problem and try to solve by one, we just take each problem by node and we decompose them. So in the objective function, we will have the immediate cost of the decision taken at the node 0, for example, plus a sum of the cost to go function, which are functions that represent basically the future cost that I will incur taking the decision in the node 0. Okay? And we have all the constraints linking to the node 0. we can generalize that, and we can make the same formulation for each node of the scenario tree. So we have the immediate cause given by the decision made at the node n, and the future cause given by the decision at the node n, and the set of constraints of the node n. So this function, this cost to go function, is calling expected cost to go function, and be in a linear setting under approximated by linear cuts that are calling Bender cuts. One of the advantages of this formulation is that now we can decompose the problem in an series of single node subproblems. And now, using this formulation, I will try to give you some ideas of how we can develop an algorithm using this formulation. So, the SDDP was first introduced by Pereira and Pinto in 1991, and it's based on the key assumption that this expected cost to go function are state-wise independent, which means that actually we don't have to approximate one expected cost to go function for each node. We actually can approximate one expected cost to go function for each stage of the stochastic process. This assumption actually reduces a lot the complexity of solving the dynamic programming formulation. And also, the assumption allows us to recombine the scenario tree because basically say that all the nodes in a stage T share exactly the same children node in a stage T plus 1. As I told you, one of the main results of this problem is that the expected cost to go function are polyhedral and can be approximated in a linear setting by the classical Bender cuts. That it means that we have guarantee that we are the algorithm will converge to the optimal solution. However, the stochastic incapacitated load sizing problem is a mixed interlinear problem with binary integer local variables. And the good point is that recently, Su et al. 2017 proposed a new class of cut based on a Lagrangian relaxation that can provide actually a good under approximation of the expected cost to go function for this problem. The key assumption to use these new cuts is that the state variables of the problem have to be binary. So the first thing that we do is actually reformulate the problem. This is the dynamic problem formulation. And we introduce a new variable in order to make a binary approximation of the state variables. The variable u actually is a binary variable that takes the value 1 if we utilize the coefficient 2 power lambda in the approximated value of the state variables. And also, we introduce a copy constraint that is the constraint that will be finally dualized in order to generate an Lagrangian subproblem. And basically, it's a copy value of the solution given by the parent node of this problem. So let me give you some idea of how the algorithm works. First, we have a sampling step when we just sampling one individual path into the scenario tree. And then in a forward step, we solve each node sampling in the previous step, solving individually the nodal subproblem with an approximated expected cost to go function. In the first iteration, for example, we don't have anything here because in the backward step, what we do is actually update this approximated expected cost to go function. How we do that? Basically, we take the solution given by the sampling node, and we make a suitable relaxation of this problem. Actually, in the paper, you can see that we can generate different kind of cuts, but we are generating, in this case, Lagrangian cuts. So we take the value given by this node, we make the relaxation, we generate the Lagrangian multiplier, and we use to generate a cut to under-approximate this function. So we move stage by stage until we reach the root node, and the solution of the root node, will provide a lower and an upper bound for this problem. So we actually have an integrality gap. So what we can improve also is that if we realize that making a binary approximation make in some way harder to solve each subproblem, we can avoid that for a while and try to make another formulation using continuous variables. And using this continuous variable, we make the possibility to generate new kind of code, which is called stress-in-inverter code, using the Lagrangian multipliers are the solution of the linear relaxation of this formulation. Also, as we have just simpler mixed interlinear programming, we can use classical techniques in OR to express in the formulation of this problem. For example, valid inequalities, we're actually including here. So this new reformulation leads us to generate a two-phases algorithms. In the first phase of the algorithms, we just generate codes to under-approximate the functions by this reformulation. And when we don't find any other code to generate, we, in this point, make the binary approximation of the state variable to generate new codes for the functions. So I will show you some computational results. We generate random instance based on the procedure of Wan et al. 2009. And we also generate a different kind of a scenario tree. In total, we have 120 instances. First, I will show you the result from Cplex figure itself. We see that for a small scenario tree up to 1,000, Cplex actually can close the gap for most of the instances. But when the size of the scenario tree grows, we see that the performance of Cplex decreases substantially. Actually, for the larger set of instances, Cplex cannot find any lower bound. And if we look at the performance of the classical SDDP algorithm, we see that for a small instance, they provide no really good gaps. But for larger instance, we see that can reduce the gap even by half that the gap provided by Cplex. So performs much more better than Cplex. And also, if we introduce the first phase that we propose into the algorithms, we can see that for all test set, we provide better remaining gaps. And also, for the larger set of instances, we can reduce even by half the gap provided by the algorithm. So actually works really well. But anyway, we see that for larger set of instances, we anyway have sometimes gaps over 20%, which are not really nice. So we still have some work to do there. Well, thank you for your attention.
All right, we have time for a few questions. Anybody has any questions? So I have a question. So I admit that the details are a little bit heavy, but there's something in the foundational formulation that's reminiscent of Markov decision processes or perhaps Bayes nets. And I wonder if that's an alternative way of approaching this problem, where you basically explicitly unroll the state space, you explicitly model the probability of state transitions, whether due to your actions or due to the environment. And then instead of using a heavy-duty OR formulation, or you pose it as an optimal policy problem. Is that something people have thought about?
Yeah. The reason we're making these cases is completely, well, it's a different approach to consider, for example, optimal policies for this problem, using, for example, Markovian decision process or in making this assumption. The problem is that as we, in the formulation, have, for example, a binary variable, binary decision, the most of the approaches making this assumption cannot actually handle this kind of model for really large scenario trees. But I know that because I talked with some experts in the field and tell me that, for example, in linear setting, they actually solve large cases, but for a mixed interlinear setting, there is some actually problems still to, I don't know, maybe I'm wrong.
It might be worth reinvestigating because the usual MDP approach is to say, in this state, I can choose one of these actions, and each of these actions then has some probability of transition to the new state. Are the transitions that you're interested in, are they action-centric, or is it just, there's some environmental process and it's not a function of the actions at all that causes me to transition to a new state?
I'm not completely sure, actually. But we can discuss later.
No, it sounds like it's very
okay.
Okay. That concludes our session today.